SwayamPrabha. Digital India. Educated India.
Hello and welcome to tutorial session for module 1. This is what we have discussed in our last lecture. We have represented our compression process on TS diagram. Then we have discussed about different concept of isentropic efficiency and polytropic efficiency. And slowly we have realized this is what is a fundamental, that's what will be giving us idea in sense of selection of number of stages. So let's try to understand that by using a numerical. So take this as a numerical. What it says, a heavy duty industrial axial flow compressor is to be designed to deliver a total pressure ratio of 3.375. The targeted efficiency for single stage configuration is 90%. So for that particular pressure ratio, your targeted efficiency is 90%. Calculate the total temperature if the stage inlet temperature is 288 K. Now, newly joined engineer has proposed to go with multi-stage configuration calculation, considering 3 stages of equal pressure ratio and polytropic efficiency of 90%. Okay. So designer would like to know what will be the resulting change of stage exit temperature and overall efficiency. It says assume your gamma equal to 1.4. So let's try to understand. Say it says we are already having our axial flow compressor. That's what is generating your pressure ratio of say 3.375, and it says adiabatic efficiency is roughly 90%. Now new engineers like you or already experienced engineer like you, he has proposed let's try to do calculation with what number of stages we have made that compressor and assume this polytropic efficiency to be 90%. Okay. So let's start with the solution. What it says, we are having our given data, that's what is for single stage configuration. Overall pressure ratio is 3.375. Our adiabatic efficiency is 90% and total temperature at the entry is 288 K. And we are looking for our stage exit temperature. Okay. So let's see. Suppose if I consider this is what is representing my overall compression ratio of 3.375. So that process we are representing on TS diagram. So it will be having my entry temperature T01 and my exit temperature as a T02. This is what is representing my isentropic exit temperature from the compressor. So how do we move forward? Let's say what all we know, we are having our adiabatic efficiency. For the stage it is known to us. We know what is our total pressure ratio. We know what is our entry temperature. So based on that we can calculate our temperature ratio, and from that we can try to calculate what is our exit temperatures. Say what is my T02 and what will be my T02s. So with this given data, let's move ahead. What we know from our fundamentals, our adiabatic efficiency for the compressor, that's what is represented by my pressure ratio divided by my temperature ratio. Okay. Here in this case, we can write down our stage total temperature ratio in sense of my pressure ratio and efficiency. Because what I know what is my pressure ratio. So let me put these numbers. So my pressure ratio we are putting 3.375. We are having our compressor efficiency to be 90%, and if we are putting that, that's what will be giving me my stage temperature ratio as 1.462. Okay. Now with this temperature ratio, we will try to calculate what will be our exit temperature. So let me write down here. We can write down my temperature ratio, that's what is given by T02 by T01. Since my T01, that's what is known to me, so I will be putting that, it's 288. That's what will be giving me what is my actual temperature T02 from the exit of my stage. It comes 420.98 Kelvin. Now let's see, we are also interested in what is our exit temperature if we are considering our compression process to be isentropic. So from our fundamental equation, I can write down efficiency as T02s minus T01 divided by T02 minus T01. This T01, it is 288 K, that's what is known to us. This T02, that's what we have calculated, it is 420.98. If we will put these numbers here, it says my isentropic temperature coming from my stage, it is 407.68 Kelvin. So that's how we are calculated if we are considering our overall pressure ratio is of 3.375. This will be my exit absolute temperature, and this is what will be my exit isentropic temperature. Okay. Now this is what is a first requirement. So I can say this is what is our solution 1. Now what it says, like as per the proposal, we will be dividing our compression process using 3 stages, and it says they are having same pressure ratio and same polytropic efficiency. It's a 90%. So this is what is been represented on our TS diagram. I can say this is what is my entry temperature and this will be my exit temperature. So how do we proceed further? Here we are looking for calculation of our adiabatic efficiency considering multi-stage configuration. So what we will be doing, we know our overall pressure ratio. Then it says we need to calculate what is our individual pressure ratio because we are considering 3-stage configuration. Once we are calculating our individual pressure ratio, we can do our calculation for my actual temperature and we can do our calculation for isentropic temperature. Once this is what is known to you, it says like designer is interested in what is the change in temperature and what is the change in efficiency. So we will be comparing what solution, what one we have done with, and next what we are going now. Okay. So with this understanding, what all we know, say for this 3 number of stages, I can write down my pressure ratio as P04 by P01. Okay. It says for all the stages my pressure ratio is same. So this P04 by P03, that's what I am representing as P04 by P03 into P03 by P02 into P02 divided by P01. What I have done, I have multiplied and divided with these pressure ratios, okay, or these pressures. P03 I am multiplied here and divided here. Same way multiplied here and divided here. Remember one thing, this compression ratio is not the addition. We have common understanding. What it says, we are talking about say compression ratio of 20, then we are adding these compression ratios. Remember, that's what is a wrong idea. Okay. So basically my compression ratio, that's what has been represented in this form. What it says, this is what I can write down my overall pressure ratio or my stage pressure ratio, that's what is been represented in sense of say my overall pressure ratio is to 1 divided by n. Let's put here what it says. My total pressure ratio, that's what is given to me, it is say 3.375. I can write down what I am looking for is say 3 number of stages. Since my pressure ratio is same for all the stages, that's the reason I am writing that as say 3.375 to the power 1 by 3. Be careful when we are doing our calculation, what instructions, that's what is given, you follow those instructions. When we are designing our axial flow compressor, it may be possible that for few stages you will be having your pressure ratio to be different. For few stages you will be having your polytropic efficiency to be different. We will be discussing how this pressure ratio and how this polytropic efficiencies we are considering for particular stages. Okay. For this numerical, we have considered our pressure ratio to be same for all the stages. We have considered our say polytropic efficiency to be same. So that's what it says. My pressure ratio for individual stage, that's what is coming 1.5. So now I can write down this is what is my pressure ratio for individual stage. It is coming 1.5, and this is what is my efficiency. That's what is given. It's a 90%. Now with this background, we can use our fundamental understanding of say temperature ratio. This temperature ratio, that's what we are representing now in sense of stage. So be careful here. This is what is written in sense of particular stage. Okay. So if I am considering my stage 1, so just look at here, say this is what is my stage 1, where I am having my entry temperature as a T01, my exit actual temperature, that's what is say T02, and my isentropic temperature at the exit is T02s. So what we are looking for is we want to calculate what is my T02 and what is my T02s. Okay. So based on that, I can write down my temperature ratio for stage 1 is a T02 by T01. That's what is 1.5 to the power this ratio. That's what is giving me my temperature ratio as a 1.136. Okay. Now for stage 1, I know what is my entry temperature. So based on that, I can calculate what is my actual temperature from the exit of my stage 1. Okay. So if I am putting this number, that's what is giving me my actual temperature from the exit of my stage 1 as say 327.16 Kelvin. Now in order to calculate what is my isentropic temperature at the exit of my stage 1, I will be using my fundamental equation. What it says, it is my isentropic enthalpy rise divided by my actual enthalpy rise. And that's what if I'll be putting my numbers, so T02s, that's what is unknown to me in this equation. I said this T01 and T02 are the known parameters. So if I am putting that, that's what it says. My isentropic temperature at the exit of my stage 1, it is 323.24. Now, like this is what is giving you indication. Okay, just look at these numbers. This is what is coming to be higher. This is what is in line to what we have discussed. My T02, that's what is coming to be higher compared to my T02s. Okay. Similar to this, I can go for say calculation for my stage 2. Now for stage 2, I can write down my temperature ratio. That temperature ratio is nothing but T03 by T02. If I am putting these numbers, because my pressure ratio is known to me and my efficiency, that's what is given to me, I can calculate what is my temperature at the exit of my stage 2. Okay. If I am putting this number from earlier stage, we have done our calculation for T02, that's what is say 327.16. And if I am putting this number, it says my temperature at the exit of my stage 2 is 371.65 Kelvin. In line to what we have done calculation for our isentropic temperature at the exit of the stage, here for exit of my stage 2, I can write down this equation for say my polytropic efficiency for particular stage, and I am able to calculate here, or we are calculating here, this is what is say my T03s, that is nothing but my isentropic temperature at the exit of my stage 2. Now with this understanding, you can easily calculate what will be my temperature at the exit of my stage 3. Okay, so here what we are doing, we are having our temperature ratio, that's what we are representing in sense of T04 by T03. We know our pressure ratio, we know our efficiency. Based on that, we can calculate what is our T04. So this T04 is nothing but this is what is my exit temperature from say stage 3, or for this case, this is what is my temperature, total exit temperature from all the stages. Now in line to what we have discussed, here I can do my calculation what will be my isentropic temperature at the exit of my stage 4, stage 3. So this temperature, that's what is coming T04s, that's what is 417.14 Kelvin. Okay, now this all temperatures, they are known to us, so that's what will be helping us in sense of doing our calculation for the efficiency, overall efficiency, when I am going with multi-stage configuration. Okay, so here this is what we are representing in sense of my multi-stage configuration. So for multi-stage configuration, I can write down my overall stage temperature ratio as T04 by T01. Okay, this T04, that's what is my say actual temperature, that's what is coming from my multi-stage configuration. This T01, that's what is 288 Kelvin, it is given. Okay, so this is what will be giving me what is my overall temperature ratio when I am considering my multi-stage configuration. Now based on that, from our fundamental understanding, we can do our calculation for overall efficiency with multi-stage configuration. So I will be putting my overall pressure ratio, that's what is known to us. Okay, so let me put that number. It says my overall pressure ratio is 3.375. Okay, and my temperature ratio for all the 3 stages, that's what is 1.467. And let me calculate that efficiency, that's what is coming 88.9%. Now what we were discussing in our class, as I told, like people, they are giving efficiency as a number. Okay, what they are saying, my compressor is having efficiency of 90%. So I told you just check with whether that efficiency what they are talking is per stage efficiency or say it's overall efficiency. Just look at, though we have considered our per stage efficiency 90%, my overall efficiency is coming 88.9%. Okay, so do not get confused with this number game. Okay, let's try to understand what exactly is happening and why we are having this difference in number. So here if you look at, this is what is a calculation for my single stage configuration where my pressure ratio is 3.375. We are having our exit temperature, what we have calculated, it is 420.9 Kelvin. My isentropic exit temperature, what we have calculated, that's what is 407.68 Kelvin. And you know our overall efficiency, that's what was given, it is 90%. Okay. Now if I do my calculation for my delta T0s, that's what is coming here. Okay, this is what is coming in sense of my what is my temperature. Here if you look at, when I am going with say my multi-stage configuration, it says my pressure ratio is coming 1.5. Same way, if I am calculating my isentropic temperature at the exit of my stage, it is coming 417.14 and my overall efficiency is coming 88.9. So here if you look at this delta T0 when I am considering single stage and when I am considering my multi-stage, that's what is giving me high temperature at the exit of my stage. Okay. So with this understanding, I am sure you may be able to solve the further numericals, or you may be able to understand what all can be done if you are doing your design, because this is what is initial starting of your design concept, because initially only we will be starting with our assumption of polytropic efficiency. We are interested in overall efficiency, but when we are doing our design, we are designing individual stage. That means we are more interested, what we say, in sense of our polytropic efficiency. Now, in order to build your confidence, let's see you do one calculation at your own in homework. This is what is your assignment problem. What it says, like industrial axial flow compressor is to be designed to deliver your total pressure ratio of 7.36. It is proposed to have 3 stages with individual pressure ratio of 1.6, 2 and 2.3. Just look at here my individual pressure ratio, that's what is not same, they are given different. Do not get confused with this. Okay, you have learned this fundamentals in the class, so you may be able to understand if I am having say different pressure ratio, what need to be done. The polytropic efficiency for first, second and third stage, that's what is say 80%, 75% and 79%. Assume your gamma to be 1.4. Calculate your overall total to total efficiency for resulting stage. What should be the polytropic efficiency of your last stage in order to achieve your overall efficiency of 78%. Okay. Consider first 2 stages, say the pressure ratio of 1.6 and 2 and their efficiency as say 80% and 75%. Okay. So, I am sure you are able to solve this numerical. Okay. What it says, you are given data with pressure ratio of 1.6 and efficiency 80%. For second stage, it is having pressure ratio of 2 and efficiency as 75%. For stage 3, it is having pressure ratio of 2.3 and efficiency as 0.79. Okay. You are looking for overall efficiency, and for stage or say for second case, you are looking for your overall efficiency to be 78%. What need to be the efficiency of my third stage? Okay. So, this is what I am sure you are able to do this part. Let me try to give you hint. That's what will be helping you in solving this numerical. Okay. Let me give you the hint for case 1. What it says, it is given with the polytropic efficiency and total pressure ratio for all the stages. So, you are able to calculate what will be your temperature rise or temperature at the exit of all the stages. Okay. And that's what will be helping you in sense of calculating your overall stage efficiency. This is what is doable. Okay. Now, in order to solve your second case, what it says, you are having your overall efficiency, that's what is given to you, and total pressure ratio for 2 stages, that's what is given to you. So, at the entry of your third stage, you know what is your temperature and what is your pressure. Okay. So, based on that, for particular efficiency requirement, you can have your stage temperature ratio for stage 3 you can calculate, and based on your understanding you can put your polytropic relation and you can calculate your polytropic efficiency. So this is what is the end of our first module. That's what is say introduction. Now we will be moving ahead with our next stage from next lecture. Thank you very much.